For our second keynote speaker, we are fortunate to have Dr. Frank van Dingelen, who is very well known to most of you. He is a principal engineer at Google, where he leads the Android core location team. He also teaches GPS. He and Professor Perenge created an online GPS course offered through Stanford University and Coursera and available on YouTube. This is a very nice resource. I really recommend it. Dr. Van Dingelen is a pioneer in assisted GNSS, the technique that allows GPS to work in cell phones. He's the inventor of course time GNSS navigation, co-inventor of long-term orbits for AGNSS, and he holds over 90 issued US patents on AGNSS. He is the author of AGPS, the first textbook on assisted GNSS, and co-editor of PNT in the 21st Century, the latest book on GNSS and navigation. He is executive vice president of the Institute of Navigation, and the fellow of the ION and the Royal Institute of Navigation. And he's also past recipient of both the Thurlow and the Kepler Awards of the ION. Previously, he was a navigation officer in the South African Navy. He obtained his bachelor's degree from the University of Witwatersrand, South Africa, and his PhD in electrical engineering from Cambridge University, England. Frank, it's over to you.
Thank you, Juan. Can you hear me?
Yes.
Great. Thank you. Well, thank you for the introduction and the opportunity to speak to you. It's a great honor to speak at this plenary, especially to follow such a wonderful talk from Dr. Arias on the very fundamental thing that our efforts all depend on. As you all know, GNSS is nothing but a clock with some features. So I'm very happy to present to you Google's use of 3D building models to solve urban GNSS problems. This talk has 7 sections. They're going to be approximately 6 minutes each, so it's fairly long. But each section will take on a new thing. So if something bores you, stick it out for 5 minutes or so, and there'll be something better following. We'll start with the problem. Then look at approaches to date. Then I'll take you into some depth in an algebraic solution for a limited case. Then show you the Google scale approach for the general case. This includes machine learning, which we'll go into briefly, and then look at the magic synergy of L5 and 3D model assistance. And finally, I'll describe the deployments by Google and the results achieved. There's at least 2 opportunities through this talk for sub-audience participation, so look out for those, and I'll point them out when we get there. Okay, so first, the problem, which we modestly refer to as the last great unsolved problem. So let's take a brief look at the last 40 years of GNSS to see why we can make that claim. So the GPS system was first built in the 70s, and the concept was and remains that the receiver measures its distance from the time of flight of the signal, and the underlying assumption back in the 70s and until today is that that signal flies uninterrupted from the satellite to the ground. So this is something you all know, of course, but let's take a brief look at how the receiver measures the time delay, because this is going to be very important to us when we get to the L5 signal. So the signal from the satellite is a carrier wave modulated by a square wave, so you get these phase changes. At the receiver, it strips off the carrier and is left with the original spreading code, the square wave, buried in noise, of course, but we just represent it here without noise in red. The receiver correlates with its own copy of the spreading code, represented here in blue. Red combined with blue gives us purple, as explained by Barack Obama. And then what you get in the receiver is this correlation response, which is a triangular response. And the single most important key feature of the civilian frequency for GPS and most other GNSSs is that this correlation response has a base of plus or minus 300 meters, because 300 meters is the distance between these bits of the spreading code. And back in the 70s, when GPS was first designed, the anticipated accuracy of the system, if you were using the military dual frequency P code, the anticipated accuracy was order of 10 meters. So we've come a long way since then. In the 80s, the situation had already changed rapidly. There was better signal processing, and with differential GPS, accuracy of around 1 meter with open sky was common for civilian users. Then in the 90s, there was a strong focus and a lot of development about carrier phase differential, again using the differential concept, but using the carrier phase measurement. And I was very delighted to hear Dr. Arias refer twice to integer ambiguity resolution, which is what's at the heart of this, which in the 90s gave us products that are now common for surveying, machine control, and so on, where we have a couple of centimeter accuracy with open sky. In the 2000s, a lot of attention was turned to assisted GPS, which is the technique that's necessary to make your GPS work in a cell phone. And the emphasis here was not so much on accuracy, but improving time to fix, which got down to a second, and improving sensitivity, which increases by about 30 dB, which is 1,000 times compared to non-assisted GNSS. And so this is standard nowadays in all smartphones, and we take for granted that when we are outside and we bring up Google Maps, the blue dot appears in about a second, and this is why. So by this century, GPS and GNSS is found in use with high speed, high sensitivity, and great accuracy anywhere where you have open sky, meaning no buildings to block the signal. Even satellites use satellite navigation, including GEOs. And if you think about it, how can a GEO use GPS? I mean, a GEO is behind or higher than the GPS satellites. Here's roughly to scale, the low Earth orbit satellites are here. A lot of them use GPS for obvious reasons. They're in the beam of the satellite. But GEOs can use GPS because they can track the signal from the GPS satellite on the other side of the Earth, even though they have to be quite specific about which satellites they try to acquire. And the signal is a lot weaker out here than it is on the Earth. But the GEOs use techniques not dissimilar to what you have in smartphones. So I just bring that up as an example of showing that the GNSS has really permeated everything and is used in literally far out examples like locating GEO satellites. In the last 10 years, there's been a lot of attention on spoofing and jamming, increased attention. In fact, you might have noticed that this week there was an article in New York Times about this very topic. And this remains a significant threat. However, there is at least one known solution to this problem if you have the means to implement it, which is to have a phased array antenna and construct beams for each channel, where each beam is only in the direction of the particular satellite of interest. So this is, of course, quite difficult to realize in practice, but the point is it's at least known and possible. And I want to contrast this with this problem that we frequently face in cities. Now imagine you are that person and you're tracking GNSS satellites, but not one of them is line of sight, i.e. in direct view. The line of sight signals are all completely blocked by the buildings, and what you are tracking are reflections. How do you solve this problem? Until recently, this was an unsolved problem, and you could not do it with any amount of money if that was your situation. You started up your receiver in that situation, you could not do this. So intellectually, of course, this is a very challenging and interesting problem, but commercially, is this an important problem? And the answer is, oh yes, this is very important. Within Google, we have a thing called the Android Customer Advisory Board, and we do surveys of our customers. So our big customers are the phone makers and the app developers. And in 2018, they told us that inaccuracy in urban areas was the #1 issue they were facing with location in general. Also from our own tests, one of which is shown in the background of this slide, based on the accuracy we know we get from phones and the number of phones there are in cities and the amount of use they get, we know that there are over 1 billion fixes per day from smartphones that are at least on the wrong side of the street or even on the wrong city block. And so what this means is that pedestrian navigation in cities is not possible in this situation, and something you yourself may have experienced. Rideshare apps such as Uber, Lyft, and so on, and including sharing scooters and bicycles, these things require sidewalk level accuracy in order to rendezvous with the customer. So I myself have experienced this often, and you may have, where you call for a Lyft or an Uber and it arrives on the wrong side of the street, and depending on the street, that might mean it's just impossible for them to get to you and the whole system just breaks down. So that makes this a very important problem and why I'm talking about it today. So I'll talk briefly about approaches to date. The oldest and best researched solution to reflected signals depends on GNSS INS integration. And this is found in cars, and automatically your smartphone will engage INS GNSS integration if it senses that it is mounted in an inertially stable way in your car, i.e. Mounted on the dashboard, for example. This is a good reason, by the way, to mount your phone on the dashboard if you're navigating with GNSS in your car. So if you do that and you drive from outside a city to inside a city, it essentially solves the problem for several minutes. You may have experienced this, that GNSS from a smartphone on a dashboard does work pretty well when you drive into a city, but the INS does not help you if you start up within the city, or you do a lot of stop-start driving, such as if you're a professional, like an Uber or a Lyft or other kind of taxi driver, or you're a regular driver in dense city traffic, or you spend too long in a dense urban environment. So this alone is not the solution. The next most researched solution is something known as shadow matching, you've no doubt heard of. I'll briefly use this picture to explain it. So what I'm doing here is making an analogy with the sun. It's just an analogy, but if you imagine that the sun is up here behind the satellite, which it is in this photograph, you can see the shadows from the sun, and someone told you, oh, I'm standing in the shadow of this building, well, you'd have an idea where they are. Conversely, if they were in the sunlight, well, you've got an idea as well. Well, shadow matching is doing the same thing with satellite signal strength, typically measured by carrier to noise density ratio, CN0, in the phone. And so with this particular satellite, there is a satellite in this location, in this example, and this is the heat map generated from the CN0. If the CN0 is weak, you'd expect to be in the blue, because that's the shadow of the buildings from the satellite's point of view. And if the CN0 is strong, you expect to be in this brownish red area. You do this for all the satellites, you can do a good job of figuring out where you are just from these shadows. So all you have to know is the difference between a strong signal and a weak signal, and there's the problem. In that location that I just showed you, here are the GNSS signals, the CN0 of the signals over a few minutes. And as you can see, there's just no obvious way to draw a line and say, well, these are the strong ones and these are the weak ones. Well, we can bring some order to this, and we've done that by using ground truth. So the blue here shows the known ground truth as we walk around this building. And then at each point, we work out using building models whether a satellite really was a line of sight in blue, i.e. it came straight from the sky, or non-line of sight, meaning it bounced off those bricks or the concrete or something, so we make it brown. And then that very same picture I just showed you, we color in the satellites blue for the line of sight ones and brown for the non-line of sight, and it looks a bit more ordered. You see blue generally on top, brown generally on the bottom. However, at any moment, you'll notice there's some blue ones here that are weaker than all the browns, and there's some brown ones that are stronger than most of the blues. And if we do a histogram of the signal, you'll see the same thing. And so what you're seeing here is that in a smartphone, there is a large variability in the measured CN0, and simply looking at strong and weak satellites is not enough. Furthermore, trees create a problem. You might have line of sight with respect to a building, but be under a tree, and that'll give you weak signals. And you see this in these histograms. And so what this shows you is that shadow matching provides useful probabilistic information, but not the whole answer to the problem. There's another technique known as 3D model-assisted pseudo-range matching, and this goes as follows. You create a grid around where you think you are, and at each point in the grid, compare the measured pseudo-range to the predicted pseudo-range, including the non-line of sight paths. So as shown here in this paper or this lecture by Paul Groves at University College London, and you find the grid point with the best fit. This technique has also shown some promise. The challenge here is computing the rays, because you have to do ray tracing, which I'll talk about more later. But in a lot of papers that analyze this, they've concluded that the ray tracing computation eats up like 1 second of ray tracing on a PC uses 1 second's worth or more of PC CPU, and it's just very computationally intensive and a problem. Also, of course, you need 3D building models with good accuracy. So in summary, the approaches to date, INS integration works great if you drove into a city, but not great if you've been in the city a while or you started up in there. And then i.e. pedestrians or cars starting up in the city, promising ideas are shadow matching, pseudo-range matching. Pretty much all the research that I've seen on this, and there's a lot of it, but all shows small trials, meaning 1 to 10 data traces in the paper, and usually in a single city. And there are many unsolved problems, some of which I've just mentioned. And bottom line, nothing deployed at scale, meaning something you could go out and find in your typical smartphone before 2020. I wanted to put up some notable research that's I'm very familiar with that I wanted to share with you. In terms of shadow matching, Paul Groves of UCL essentially started that about 10 years ago, has written about 70 papers, so by far the best published in that area. UC Santa Barbara, a group led by Andrew Irish, subsequently moved into Uber, did something called shadow mapping, which is shadow matching plus SLAM. And then there's other references there which might be useful to you. This is by no means comprehensive, but if you start with these authors and then follow from their references, I think you'll find everything that's out there. Okay, so now I want to turn to a particular solution, which is a complete solution, but for a limited case. And the limited case is knowing the reflectors, knowing which buildings the signals are reflecting from. And we need to know this because we have, underlying all of this work, is a chicken and egg problem. Let me explain the chicken egg problem first. The non-line of sight errors or the reflected errors are a function of your position. That's the one. If there's anything you take away from this talk, you should take that away. If you think about it, when you're standing in a street and you're measuring a reflection, if you move, the reflection changes. If you move away from the building, the reflection from that building gets longer. Conversely, if you move closer. So if you knew your position exactly, then you could work out those reflected errors and you could remove them and you could compute your position. So there's the chicken egg problem. We don't know our position. But that very problem, if you express it in math form, gives you a solution. If you say, well, these non-line of sight errors are a function of my unknown position, XYZ, and I write an equation for that, well, then I've got an equation in XYZ and I could solve for XYZ. And I'll take you through how we do that. I will do a 1D case, then 2D, then 3D, and then show you the solution. And then finally, I'll show you an equivalent solution, which involves reflecting satellite positions around the plane and creating something called virtual satellites. And I'm going to show you that because it's kind of interesting and it involves a really important subtlety that might not occur to you right off when I first show it to you. And this is the first chance for some audience interaction, so stay alert. Okay, so let's go look at the 1D case. So imagine in 1D, there's a satellite out there to the right. You're standing there. The unknown in this case is delta x. That's the thing we're trying to figure out. Where are you in this 1D space? The known values are x sat, the position of the satellite. We'd get that from the ephemeris or from the assistance of assisted GPS. And the range or pseudo-range measurement, which here is line of sight, so we've labeled it PLOS. So just imagine this very simple example, and you asked to solve that. Well, clearly the answer is delta x is x sat minus PLOS. So if you follow that, congratulations, you are now a navigation engineer. Let's bring in a building. So now let's just suppose as a thought experiment that that building manages to block the line of sight, and by some magic, the non-line of sight signal sneaks by the building and bounces off the building behind you and arrives back. Now, clearly this cannot happen in one dimension, but there's just a way to think about it to get us going, and this will get more realistic as we proceed. So now, the unknowns are still delta x, but PLOS is now unknown because you can't measure it because it's blocked. And the knowns are still the position of the satellite and PNLOS, PNLOS, the non-line of sight measurement. So now what we do is we just write the unknown, PLOS, as a function of the known measurement and the thing we're trying to solve for. And you can clearly see this is the relationship that the P line of sight is P non-line of sight minus 2 delta x, because the non-line of sight has to go past you and come back. So now we have our unknown value written in terms of something we know and the thing we're trying to find, plug that into the original equation, solve for delta x, and you're done. And just try and remember this, there's a minus 2 delta x in here. You'll see that again later as we get more realistic. Okay, so in 1D, you can solve this problem. In the 2D case, now the two dimensions here are x and z. Now the satellites have some elevation. The elevation of the satellites is known and essentially the same for the line of sight ray and the non-line of sight because the satellites are so far away that these rays are practically parallel. How close? They're within 0.0003% of being parallel, so we can assume they're parallel and it doesn't change our result by more than a fraction of a millimeter. And so we know this elevation. And by some geometry shown on the top right here, which I won't go through, but I think it's quite easy to see and believe that multiplied by cosine of elevation puts this, gives you a projection onto the horizontal, and you get back to the 1D case, which we just solved. So you have this delta P, which is the difference between the non-line of sight and line of sight, as defined there, is just the 2 delta x with now the cosine elevation term. And of course, if elevation went to 0, we revert back to what we had the previous slide. So now I hope you get the gist of where this is going. And with 3D, you have a slightly more complicated picture. Now the rays are coming out from behind your screen towards you. If we set up the coordinate system so that x and z are the same and y is in line with the building, then the azimuth with respect to the building is that angle there. And so now I think you can see that multiplying by sine of azimuth is a projection onto your screen. You're back to a 2D solution, which from then with the cosine L takes you back to 1D and we're back to a solved problem. And again, you can see here, if you set L to 0 and as to 90, you get delta P equals 2 delta X, the original 1D. So you see how we build this up. And then if we go to the 4D algebraic solution and work through the math, which I'm not going to do, the classic nav equation, which many of you will be familiar with, you've got your pseudo-range residuals here. You've got this line of sight vector, which is represented here. So this is the first term, second term, third term. And you've got your common bias, delta t here, and a 1 there, and a matrix like this. This matrix equation, which is true for line of sight signals, just with this modification, which I derived from the stuff I've just been through, gives you a closed form solution for non-line of sight signals. And now, even if all the signals were non-line of sight, if you filled in these rows appropriately for each satellite, you could solve this problem. So I thought that's nice to show you because it's a technical meeting. There needs to be at least some math in it, I think. And here's an alternative and equivalent approach to show it, which in a way is even more elegant than what I just showed you. If you take that same situation and take the real satellite and then construct a virtual satellite by reflecting this ray about the plane that it's bouncing off. So now we get this virtual line of sight. If you do that for each of the satellites and then treat the virtual satellite as if it were a line of sight satellite, it then solves the problem in the classic way, that just using classic GPS techniques. Okay, however, there's an important subtlety. Do you notice these asterisks here? The subtlety is that the normal GPS solution, you have to take into account the amount of time it took for the signal to leave the satellite at transmit time and travel all the way to Earth and get to you at receive time, which is some significant time later, about 70 milliseconds. And in classic GPS, you have to rotate the reference frame of the Earth to account for that passage of time. And so you have to work out your position at the time of reception. And if you don't do this, by the way, the Earth will have rotated by 20 to 30 meters, depending on where you're standing, in that amount of time, and you'll get the wrong answer. So when you come to reflect the plane, so this is the audience participation part. Here's a little quiz for you. When you're reflecting this satellite around this reference plane, what reference plane are we talking about? Is it the reference plane at the time of transmission? Is it B at the time of reception? Is it the average, or does it make no difference? So I encourage you now, if you think you know the answer, use the chat in Zoom. Put in the chat, if you're feeling bold, send it to everybody. You can prove that you knew this all along and get some brownie points. And I'll give you a chance to do that, or share with your friends, or just write it down on a piece of paper, or just remember what you thought. And the answer is B. You must use the reflecting plane location at the time of reception. I'll briefly walk you through why, because it's an interesting thing to look at this subtlety of GNSS. And it's like many things in GNSS, something that's perfectly obvious when you first look at it, and the more you think about it, the less obvious it gets. And that's what makes our subject so interesting. So the satellite sends the signal at time of transmission. So clearly that's what we care for about the satellite, is where the signal came from at the time of transmission. And then the signal travels to the Earth. During that time, the Earth's rotating. So when the signal arrives at the building is at the point where it's going to be at the time of reception. So the only thing that matters is where is the building at the time of reception. Where the building was at the time of transmission is of no relevance to anything. And so that's the answer. Where is the building at time of transmission? At time of reception. It's where is the satellite at time of transmission? Where is the building at time of reception? Now, if you got that right, pat yourself on the back. Remind your friends. And if you notice that there's actually another subtlety on the subtlety, which is that strictly speaking, it's really where is the building at the time the signal hits the building, not the time of reception, which is where the signal gets to you. However, that slight difference of the time of hitting the building to you is typically around 2 microseconds in typical city geometry, and the Earth rotates less than 1/10 of a millimeter in that amount of time. So we can safely use time of reception for our calculations without making any difference to the noticed results. So in summary, for this limited case, either using the substitution of the known measurements for the unknown measurements and making them a function of the unknown, delta x, or using a reflected satellite position, and in either case correctly accounting for the Earth's rotation, we can solve this problem, which at first glance seemed insoluble. So that's great. However, so are we done and can you go home? No, we're only halfway through, because unfortunately, there are several things that break the assumptions that we just used in that exercise. Number one, there are many different reflectors for each signal. If you're used to seeing a diagram that shows you a single reflection, such as I drew by hand in the previous slide, those diagrams are very misleading. This picture here is not a hand-drawn diagram. This is actually from Google servers where we do this for real. These are all the rays from a single satellite. These rays going out to space are not going to many different satellites. They're all converging on a single satellite. This is how many rays you get converging on a typical location in a fairly benign city environment. This is the medium rise part of San Francisco. When you go into the high rise, it gets worse, as I'll show you later. So you get many different reflectors from each signal. Also, the reflectors are not mirrors, but they are scatterers. And you can kind of see this here, that there are many different paths that converge on the same path. This could not happen from the mirror, but buildings are not typically mirrors. They scatter the signal, and so you get even more rays than just the rays you would get from many different buildings. Now, each of these two is not fatal to the math we just did. You could expand that math, and it's actually an interesting area of research, if any of you are looking for something like that, to add in all these different terms to what I just showed you. However, the third thing really does kill the previous approach, which is often, actually usually, we don't even know what street we are on in the first place. And this example that I showed you before, this was the background to an earlier slide. The red here is the ground truth, and the green is from a smartphone. This is very typical. This is a high-rise part of San Francisco. So here, for example, we're almost in the wrong city block. And particularly, we'd think we were on this street if this was the position, the raw position from your GNSS receiver. So if we were to use the technique I just described, we'd be using these reflectors, which are the wrong reflectors. The signal is not reflecting off these north-south facets of the building. It's reflecting here. And so we need something more general than known reflectors. And so that leads us into the more general solution, which we've implemented at Google and which I will walk you through now. So first off, you need 3D models. We have them in abundance. If you played around on Google Earth, such as that image there on the right came from Google Earth, you'll get a feel for what Google has at its disposal. We've deployed 2 phones, 3D model assistants, for approximately 4,000 cities, covering all major cities in North America, Europe, Japan, Taiwan, Brazil, Argentina, Australia, New Zealand, and South Africa, and we have ongoing testing in other places not mentioned here. Next up, you have to have a means of doing ray tracing that's feasible. Now, if we look at, so here is downtown San Francisco, and let's look at it from sort of up in the stratosphere. The rays from the satellites look like this and looks fairly simple, but this picture on the left belies the incredible complexity that arrives in the labyrinth of the city. The picture on the right is the same picture as on the left, just zoomed in. And what you're seeing here are the actual rays that converge on a single location on the ground in the city. And so each bundle of the same color are the rays from a single satellite that find their way to a single location. So you can get an idea of the complexity by that. And from the numerics point of view, it turns out that if you have M satellites, so typically that's a number like 20, if you're doing this over N by N grid, where N here would be something like 100, and you have P rays. Now the rays here, when you're doing ray tracing, it's all the possible rays you have to consider. So P can be a very large number, like in the thousands. This problem is an order M n squared P cubed computation problem. Now, typically, with computing and coding, we try to avoid order n squared problems, like a nested loop is something you try to avoid. You definitely don't want order n cubed problems. This is worse than an order of p cubed computation problem. In plain English, this is not going to run in your phone if you don't do something quite smart to simplify the problem. So that's necessary in order to make this work. Some way of doing ray tracing that's more than just the typical and traditional way. And then you also need raw GNSS measurements, and luckily we've had that in Android phones since 2016. Many of you will be familiar with this, and you can get raw measurements from all GNSS satellites, and this is mandatory and standard now in all new Android phones. So the way we do the implementation is we use all of the above, the best of the published research. We're lucky enough to have worked very closely with some of those researchers I mentioned earlier. We also use our own Bayesian approach to deal with variations in the measurements, such as I've discussed. And most importantly, we use machine learning, which I will discuss in the next section. But just before getting there, seeing as I mentioned raw measurements, I did want to do a brief aside and shout out for something else that Google and Android is doing with the raw measurements from the phone. Is a thing we've called the decimeter challenge. And this is an opportunity for anyone to access a collection of raw measurements that we've collected ourselves at Google from phones and cars, driving many hours on highways and city streets. We also provide base station observation and very precise ground truth reference to the phones, so that you can take this data in the way that in computer science, often data is shared so people can compare results to a known data set. And so instead of you comparing your results with your data to someone else's results with their data, now you can compare results with a standard data set. So that's something we've done just because we think it's a good idea for the community. But we also have this competition, which is the details are on the ION website, and there will be a session at ION GNSS in September in St. Louis, where I hope we will all be in person post-vaccinations. I'll see you there. Now, back to the urban problem. Oh, just by the way, that if I go back a slide, this decimeter challenge, this is all about open sky use of measurement and using the carrier phase that you get from the phone. It's very different from the topic of my talk today, which is all about urban canyon. So if you like, we stepped out into the open sky on this slide, and we'll step back into the urban canyon now. So in 7 minutes or so, what can I tell you about machine learning? The goal of this section is to give you a brief idea of what it's all about. If you're familiar with machine learning, you should follow along and maybe pick me up on where I describe it badly. If you're not familiar, my goal here is that you could get, over the next few slides, get an idea of why it is that machine learning can work and does work to compute GNSS location. And if you can come out of this just believing, oh yeah, I can see how that works, then we've accomplished the goal. So, preamble to machine learning is, first of all, it's really important to think properly about GNSS. And this very common notion of imaginary spheres emanating from a satellite to give you your distance from a satellite, that is not helpful. So forget about that and imagine that, well, we know approximately where we are, at least to the, a couple of city blocks. And imagine that you overlay a grid on the ground and say, well, I'm somewhere on that grid. And let's think about the residuals at each grid point. So a residual is just the measured minus the expected rays. And if you're at a point where the measured ray matches the expected ray, well, that gives you this line of position with the residual 0. So something you might be familiar with, and it kind of takes us back to classic navigation, where if you had no clock error, that line of position would contain your position. Generally, you do have a clock error though, so let's put that aside for the moment. So if that's the line where the residual is 0 and you move towards the satellite on your grid, well, then the expected range will get smaller, so your residual gets bigger, and conversely, you move the other way, your residual will get smaller, more negative. Okay. So as a little example, what we call a toy example, we've taken real measurements that were collected in open sky, just looking at the measurements for 4 satellites, and constructed a grid around about the approximate position, and actually computed the residuals at each point and plotted them here with a heat map. So red is more positive, more blue is more negative, and so this is the grid, and our real position is in here somewhere. And this is another picture of the same area, but for a different satellite, and this is for a different satellite, and this is for a different satellite again. So if you look at this, you say, okay, well, this satellite, the azimuth is 2, so it's in the north, the elevation is 6, it's low. So basically, as I move one grid step towards the satellite, my residual changes by 1 grid step at each time. I get these nice straight lines, looks like a flag, all right? If the satellite's down the bottom right, well, the lines go like this, and so on. This one's interesting because the elevation's almost directly overhead. So now as I move around my grid, the expected range to the satellite changes imperceptibly, and so this grid is all the same color. But if you just look at this and understand that I took out the clock bias in advance to make it easy for us humans to see what's going on. So there's no clock bias, so the residual equal to 0 would contain the true position. So this is the second chance for audience interaction, and because you're sitting in front of your own screens, I invite you to put your finger on the screen where you compute that the true position of this receiver was, and I will show it to you in a second. All right, you got that? You're all touching your screens, and the answer is there. The true position is in row 2 and column 5 of my grid, where all those residuals were 0. So now imagine I had not removed the clock, and that all these residuals, instead of this being 0, instead of this line being 0, this would just be a plane. It is a plane. All these residuals form a plane on top of the grid, but this 0 would not be 0. It would be some other value which would be equivalent to the clock bias. The same with this plane, same with this plane, same with this plane. What you've done here is you've intersected the planes. And so that's a good way to think about GPS for this problem, or GNSS. That what you're doing is finding the solutions to the intersection of planes, and then that includes the clock bias. It's the same solution. I hope you all see that, because that leads us into machine learning, and we're going to look at, well, how could you teach a machine that finding the intersection of the planes is what it should do without actually programming it to solve for the intersection of planes. And so I'll briefly describe what a neural network looks like to give you the idea of how that's possible. So a neural network is just a connection of inputs to outputs through a lot of nodes, and these nodes are called neurons for the analogy of the brain. It's just an analogy. These are not like the real neurons at all. Think of them as just nodes, but they're called neurons. By the way, each term of art, each term that's common in machine learning, I've put in italics. So at least you go away here with some vocabulary. So each of these neurons connects to some combination of inputs from the previous layer and has an activation function. What is an activation function? Simply a nonlinear operation. And with lots of these nonlinear operations cascaded, you could form any function. For example, you could form the absolute value if that was the thing that you needed. And in the way you train these networks is you feed in all the inputs. Our inputs would be the residuals that we've been talking about, and you give the network the answer. You give it inputs and you give it the known ground truth. That's the output, the position. And you do this for millions of examples. And it learns what paths through this network correspond to the ground truth. And then I hope you can imagine that by doing this, it could figure out, oh, I see, the path that corresponds to subtracting this residual from that one and discovering that they equal, that gives me the answer. And by learning that, the network has learned to intersect planes. Without you ever telling it, you have to intersect these planes to get the answer. Okay, so what this actually looks like, so this previous picture was a representation of these neurons. When you actually code this up, this is shown, the way you show what you've coded is in blocks like this, and each box here really represents a lot of neurons, just like I showed you, and the width of the box and the depth represents something like channels in a GPS receiver. So if you imagine the inputs here are all these different residuals, then it literally corresponds to the channels of the receiver, but you can have any channels you like. We might decide that every adjacent grid point is a channel, and we'd look for the relationship between the residuals at one grid point and the residuals at another grid point. And so you can build these up anyhow you like. This was the particular network we used for this particular toy example to actually do it in real life, so I could show it to you. So we give the inputs or features in machine learning talk are the residuals for our simple example. We feed in millions of examples. At each case, we give it the XY, I just did it for 2D, of the user location, and it learns the paths through the network, and that's called training the network, and the result is called the model. So now we have a machine learning model, which just means the known and preferred path through the network. Then we give it some fresh data that it's never seen before, and this is the result. Give it a few minutes of GPS data, it came up with these blue dots scattered around here, and then for comparison, I did a least squares solution on those same measurements. I got the red dot. So you can actually see that this simple network has a slightly tighter scatter or less covariance than the least squares solution, although it does have a biased solution. So that's interesting. You start to get interesting characteristics of your results that don't correspond to your a priori ideas of how least squares should work. So I know some of you are saying, so what? I already know how to do least squares. But the point of this is not to build a neural network that can improve on least squares. The point is just to show you how it's possible that this can work, because soon we will get to something where we don't know out of our own brains how to do it in the first place. So I just want to touch on a couple more things that of machine learning that'll make it give you some notion of how this works in urban canyons. There are these different, I described at the input you have things like the residuals, and the output you have user location. What are these ones in the middle? Well, these are called hidden layers in the vernacular, and between each of these, you have a set of weights, and the network can learn different weights. It'll try different weights to figure out what are the best weights and what is the best path to collect my inputs to my output. And if you imagine more inputs than just residuals, let's imagine that we also add to the network inputs which are CN zeros. Well, we know from the physics of this that with stronger CN zeros, we'd expect the residual to match better, and with worse CN zeros, we'd expect the residual to match worse. And if we did this in the classic physics way, we'd do a weighted least squares, or we'd do weighting in a Kalman filter. Well, the network's going to learn a similar thing. It's going to learn that the weights that where the input was the CN0, and where that meets up with the residual from that same satellite, that if it weighted that stronger for the strong CN0 and weaker for the weak CN0, it more often gets the correct answer in the training examples that we give it. And so that is to explain to you the weights and these so-called hidden layers. So you put this all together in a real life example. So now we're going to move beyond the toy example and to real life. And so now we're in reality. So in reality, you don't have a flat plane, you have 3D terrain, but we know the 3D terrain. So we overlay our grid on the 3D terrain. Imagine taking a blanket and laying it on top of the 3D terrain. We also have the 3D buildings, as I described, and we also have many more features or inputs than simply residuals and C and zero. For example, there's different constellations, so each of them behaves slightly differently. There's different signal types like L1CA, E5A, and so on. Each of those behave slightly differently. And there's many more features or inputs which I can't get into now. You put those all in, now you look at the heat maps. Now if I ask you to put your finger on the true position, not so easy anymore, is it? But you can imagine that if I feed in millions of examples like this, and with each example I have a known ground truth, well, again, the network can learn what's the right thing to do. And this is where the machine learning can surpass human intelligence, because for us, it just becomes impossible to know what is the combination of all these things that corresponds to the right result, given the complexity of these many scattered rays that I've showed you, and the varying C and zero, and so on. So we do all that, and here's an example of the result. This is showing you in brown the native GNSS location coming out of the dual frequency L1, L5 GNSS chip in a smartphone. And as you can see, it's usually on the wrong side of the street or worse. This is in Berlin, Germany, by the way. And the worst case error in this short walk is 50 meters. So this is fairly typical in this environment. And doing what I just described, the machine learning plus 3D model assistance, we get locations that very closely hew to the ground truth, which is shown there in the black and white dots. So that's just one pretty example for you, but I'll show you full statistics in section 7. Okay, so I hope that gave you a notion of machine learning, and if you already know about machine learning, I hope I explained it to your satisfaction. Now, let's talk about L5. Okay, why am I specifically picking on L5 here? Didn't really spend much time on L1 or L2 or anything else. Well, L5 and 3D model assistance go together like rock and roll, bread and butter, bed and breakfast. I'll show you why. The key feature of all L5 signals is that they have a 10 times higher chipping rate than the corresponding L1 signals for that constellation. And so the correlation peak that I mentioned right in the beginning is 10 times narrower than it would be for the L1 signal. And that is the single most important thing about L5. In itself, that's a good thing. Without anything else. In the open sky, that's a good thing because you get more accurate measurement from L5. But that's not nearly as powerful as the magic that happens when you combine L5 with 3D model assistance, because when you get in an urban canyon and you get reflections, if the signal is blocked, so if you imagine this green signal is blocked and you're just picking up the blue from a reflection, what we see is that when you get one reflection, you get many. And you've seen this in every picture I've showed you of the actual rays. You've seen that there are many different paths in a big city. There are many paths from a single satellite to a user. So you almost never get a single reflection. You get multiple reflections. And with L1 in GPS, for example, the peak width is plus or minus 300 meters. These multiple reflections all overlap. And what many of you will be used to seeing is this kind of multipath picture. And you see this, you see, oh, I get it. There's a correlation peak. There's another correlation peak, another correlation peak. The actual output of the receiver is some blob like this gray. That's bad enough. Because by the way, keep in mind, the distance from this little sub-peak to this peak is about 100 meters. So that's a big error. This is bad enough, but this static picture is not nearly as bad as the reality. And unfortunately, in papers, we can't print GIFs, but on a screen, I can show you a GIF. The thing to realize here is that these different signals have different phases and slightly different Dopplers from each other. Even if you're stationary, they have different Dopplers because the satellite is moving. And so this GIF shows you a representation, a real-time representation of the constructive and destructive interference between these overlapping non-line of sights from a single satellite. And so what you can see is that it's actually impossible to predict at a specific time what the receiver should be measuring. Because at this moment, it'll be measuring the signal here, and a few seconds later, it's going to be measuring something 200 meters away. And so it's only possible to model L1 in a statistical sense where the variance on the statistics is 50 meters or more. Whereas with L5, we frequently have, most commonly, we have distinct peaks, at least distinguishable peaks. Even if they overlap a little bit, top of the peaks are distinguishable, and therefore you can predict the delay with great certainty. So that is the magic of L5. So in summary, L5 alone is not going to solve the non-line of sight problem because there's still a bias with an L5 measurement. It's just more precise. But it's this precision that gives us the magic because we can use it to model the reflection, even multiple reflections. And so 3D model assistance plus L5 provides the solution that we really want for non-line of sight signals. Okay, and so finally, and if you made it this far, congratulations. And I'm briefly going to talk about actual deployments that have been done in phones and the results that we get. So 3D model assistance has been launched by Google on 3 different clients. The first one is on Google Map Live View. Live View is a feature of Google Maps that's shown here in this little video, where instead of looking at a 2D map and trying to interpret that when you're in a city, you lift up the phone and it'll automatically bring up this, the camera and then show you augmented reality overlays to tell you, turn right here, as you can see she's looking at. And this works partly by using vision as for location. So part of this solution that you see on the screen here actually uses the combination of what the camera is seeing and Google's Street View images, which you probably all know about, and which so we have a very good idea of what each building is. So that's navigation in the oldest way. You know, you look around you. But to make this work properly, you have to have an idea of which street you're on in the first place. And so 3D model assistance is a really key part of initializing this whole system. And so for this particular implementation, the live view makes use of server-side processing. And so all of this ray tracing and everything we can do on a server. And so we're almost unlimited in terms of processing power. And so we can deploy the most powerful solution. And we get something like I showed you in that Berlin example. And we cut down the wrong side of street events by 90% from before using any kind of processing. So we have 90% fewer wrong side of street events than the GNSS native output. Then in March of last year, we also released an on-device version. So this is a lighter version of the above, where we're not making use of the server, but we're actually doing processing on the phone. And we're providing corrections to the chip to give the GNSS chip information about the reflections so that it can improve its position. And then we also fuse the results in the fused location provider, which is the part of Android that gives you the combination of GNSS, sensor inputs, Wi-Fi, and so on. And by doing this, this was on all Android phones of version 10 and beyond. And this reduced wrong side of street events by 50%. And I said I'd show you early on when I showed you that single example in Berlin, I said I'd show you proper statistics. So when we give you these numbers, this is not from 1 or 2 different cities. This is from tests that we conduct. We have operators all over the world who do nothing but go out every day, 5 days a week, and conduct tests against known ground truth. We do this in 20 cities over 4 continents every day of the year, every weekday of the year. So over 1 million data points, we get these statistics. And then just last month, we released V2. What makes V2 different from V1 is just V1 was the first version that could run in a phone and gave significant results, such as 50%. And so we put that out. V2, I can't go into the details of what makes it better, but you can imagine with time, we're adding more and more into the phone. So this was released on Pixel 4a and Pixel 5. And gave 75% reduction in wrong side of street. And there's an example showing you the native GNSS position from one of those phones, from a Pixel 5, and then with 3D model assistance, what you get when walking down the street and across and back. There's a blog. You can just Google Android developers blog, urban GPS accuracy, and you'll find a lot more detail about this. And then finally, what's coming next? Well, in this quarter, we will have the V2 on-device corrections for the entire Android ecosystem. So that means not just Pixel phones, but Samsung, Xiaomi, etc. For any phones with operating system 10 and above, Android 10 and above. And then later on this year, we'll release so-called V3, which exploits this magic of L5 that I've been talking about. And so thank you if you've stuck with me throughout all these 7 sections. That's all I have, and I'd be delighted to answer any questions. Thank you.
Thank you, Frank. We have a couple of questions ready for you here. Gabriel asks, in slide 44, is it possible to compute this machine learning solution in real time, or was this done in post-processing? How long to get one pose with all the features and inputs?
Okay, good question. So the answer is yes, it is possible. And but for this example, this was computed using the server implementation. And so when I explained V1, V2, V3 here, and the live view implementation, so the live view is this. Let me bring it up here. This is a feature that uses a server connection in the first place to do the image processing and the alignment with Street View. And so you're making a connection to the server anyway. And so in this case, we use the machine learning. And it was one of these cases that I used to show you the result for the Berlin. And by the way, so that raises the question, well, was this blue dots done by alignment with Street View? The answer is no. This was before. These blue dots are simply GNSS. This is without use of sensors, without use of image matching. Once you do that, those blue dots will get better. They'll get closer than they already are to the white. So this is showing you simply the machine learning approach on the server with GNSS measurements only. Okay, then to answer, okay, what would it take to put on the phone? What I can say about that is that's one of the reasons we're doing V1, V2, V3. With each version, we bring more and more of what's on the server into the phone, and the exact details of how much more I can't say. But I think part of the question was how long does it take? We make sure that anything in the phone takes a small fraction of each second. We're only spending a small fraction of that second in the CPU, so the phone doesn't get hot and run your battery down. So anything that we deploy in the phone is only deployed once the processing time is a small fraction of the update time.
Okay, our next question is, thank you very much for this excellent presentation. My question concerns the machine learning part. Do you think these kinds of techniques can be implemented for safety critical applications such as self-driving cars? Isn't the difficult process of certifying a localization function based on machine learning a brake on the deployment of deep learning networks?
Yeah, so good question. I'm not really qualified to answer the question about self-driving cars, though I will tell you, like, machine learning is what is used by everybody who does self-driving. So for that, and maybe a future ION, we could get somebody from Waymo, Google self-driving cars, to tell you more. But certainly it's true that in terms of certification, machine learning presents its own problems because as you've seen with games like chess and Go, these games where there's been famous machine learning, the neural network will do things we humans actually don't know what it's doing, and that's the whole point, is that it's doing something that we don't know how to do. That's why it can always beat us at chess and now at the game of Go, and why it can do 3D model assistance better than we can. So how that ties into certification is something beyond my expertise. I don't want to say anything about, because I'm just not qualified to say that. All I can say is, good question. Machine learning is used by self-driving cars, and the certification issue is an issue.
Okay, great. The next question concerns E911 calls. Can you comment on Z-axis precision provided by your approach, especially in regard to the FCC's 3-meter 80% Z-axis precision requirement mandated for E911 calls beginning in 2024?
Yes. So just to kind of summarize for people who may be not so familiar with this, E911, when it first came in the 90s and 2000s, was about providing the XY position of the phones. And of course, a lot of calls are coming from buildings, and so knowing which building you're in is fine, but you know that still may take somebody an hour to find you if you're in a tall building. Which floor are you on? So there's a new mandate that says within 80% of the time you must provide the altitude to plus or minus 3 meters, which will give you a couple of floors, which is better than 50 floors or more. And so that's the mandate. And the question asks our solution. So the 3D model assistance with GNSS is being implemented by Google. So far, it's for pedestrian use cases when you're outdoors. And that's it so far. It's not for use indoors. For indoors, by far, the best way to locate yourself is to find transmitters that are indoors with you. Luckily, there are millions of those, actually over 1 billion. They're called Wi-Fi access points. There's one right there behind me. All smartphones make use of SLAM techniques to learn where those access points are and make use of them. And that's part of the right solution for indoor location, including Z-axis.
Great, thank you. Our next question is from Brian, and he asks, what are the main considerations for server-based processing versus phone-based processing?
What are the main considerations for server versus phone? Okay, good question. And I think I can give you a concise answer. So why you would want server-based is you effectively have infinite processing power on the server, especially if you're Google. That's why you want it. What's the drawback? It takes data. That's the #1 drawback, and battery life. When your phone's using LTE or 5G, it's going to consume your battery, as you all know. If any of you are watching this presentation on your phone's probably feeling quite warm right now. So you don't want to use the network more than you have to. One thing I never got to in detail is that when we've deployed the deployment on device by Google has been done using geofences. So we've geofenced the areas in those 4,000 cities where the tall buildings are. So if you're using an Android phone and you're somewhere away from tall buildings, it will not invoke 3D model assistance because we don't want to get anything from the server that's not really necessary. And if you're in an area with tall buildings, we'll cache the models of the building the first time you're there. Just like if you use Google Maps, it'll the first time you use Google Maps in here, it'll cache the map and then it won't use it again. So we go to great lengths to make sure we use the server as little as possible because the consideration is data and battery life. So I think those are the main considerations for why not to use the server. So I think that's the answer. It's infinite processing power versus data use and battery life of the phone.
Great, thank you. One other question. Would the ray reflection method work well for carrier phase, since there could be a phase change at the reflection according to Fresnel equations?
Yeah, so I understand the question. I think that could you use this for carrier phase? I think the answer is no, because we don't know the building facades nearly well enough to deal with carrier phase type of accuracy. So typically our building models are accurate to about 1 meter, which is great for what we're doing where we're trying to solve problems of wrong city block. But if you're trying to use a reflection for carrier phase, you'd have to know the location of the reflector to better than a wavelength. So that would be better than 20 centimeters. And that's just something that's unknown. So I actually think there's almost a kind of Heisenberg uncertainty around use of reflections with carrier phase that almost impossible ever to know what the phase of a reflected signal would be, because A, you'd need to know the location of the reflector to a small fraction of a wavelength, and you would need to know the scattering characteristics of it. I mentioned scattering a couple of times. These buildings are not mirrors. Occasionally you'll have a building that's a mirror, but usually it's not a mirror, it's a scatterer. And I think it's almost impossible to be able to proactively reconstruct a signal with any knowledge of what happened to the phase because of that scattering.
Okay, thank you. Our next question says, you mentioned using the server-based processing that you mitigate around 90% of the wrong side GNSS events. What kind of cases or challenges do the other 10% fall under?
Okay, good question. Yeah, why aren't we done yet? The challenges are the challenges I addressed along the way. The CN0 varies a lot, so you know the contribution that shadow matching makes is limited, and then the pseudo ranges themselves can find areas that spoof you where nature spoofs you. So when you do this grid search that I've talked about, there'll be an area. Let me bring up this picture. Like if I ask you to put your, you know, as I did, I said, well, put your finger on, so these colors mean something. If I said, you know, so I can't go into detail about what they all mean, but they mean something. But if I said, put your finger on the area that's most red, well, different people have different opinions of what that is, and whatever you pick, most red, most white, most blue, you'll see that in some areas, there's red hotspots up here, in other areas it's down here. And so what happens is, at the true location, the model should match the measurements, but in a large enough grid, there's going to be somewhere else where what you modeled at that area by coincidence matches what you measured somewhere else, and that's the big challenge. And that's that accounts for that last 10%. That there just happened to be somewhere where, when you do all of this, it finds a spot, it finds a position where the model fits the measurements better than the true position. It just happens to be the wrong position.
Great. We have a question from Demetrius, who says, what about the conversion from right-handed circular polarization to left-handed that occurs with each reflection? Does Android accept only RCP, or will it do both?
Okay, the answer is it does both, because in cell phones, the antennas, the GNSS antennas on all cell phones are terrible. I'm sorry to say. There's about 15 antennas inside any smartphone. If you stop and think about it for a moment, you'll see why, right? You've got Wi-Fi. You all know that Wi-Fi comes in 2.4 and 5 megahertz. You've got many bands of cellular. You've got Bluetooth. You got GNSS, which now comes in 2 bands. So there's just antennas everywhere. So the GNSS antenna has very little space, and what you like is you'd like something like a quarter wave antenna. Well, you're not going to get it in a phone. There's not enough space. So we don't have properly polarized antennas in phones, and they're essentially linearly polarized, and they really can't tell the difference between RCP and LCP, unfortunately. But what it means is that the phone really treats both pretty much the same, and so it doesn't come into these calculations. I think if it did, by the way, if you did all this for a car implementation with a patch antenna on top of a nice substrate where you had circularly polarized, then you could make use of that in a smart way, and it would help. But for phones, it's not a factor, unfortunately.
Okay, one other question from Andre says, how does the system cope with an evolving urban landscape, such as the construction of new buildings?
Great question. If your model's wrong, the solution's going to have an error in it somehow. And so the way the system copes with that is we try to keep our models up to date. And as I mentioned, when you're in an area for the first time, it'll download a 3D model of the buildings. So by the way, it'll cache up to 20 megabytes. If you're wondering, like, how much is that? That's about 3 photographs. So if you post 3 photographs on Instagram, you've used up as much data as we're going to use in any city on your behalf. And then it'll keep that data cached until we refresh our model. And the next time you're in that same city and we know there's a refreshed model, we'll push a new model. So there's other things that you can imagine that I can't really talk about yet. But the basic way is you keep your models up to date.
Okay, thank you. Going back to that 10% solution question, with multi-constellation receivers, can the 10% GNSS events be reduced even further? Are the challenges algorithm improvements or more input?
Yeah, so the challenges, as I mentioned, are this like that you get spoofed by nature. There'll be a spot that seems better than the truth in terms of how the models match the measurements. Everything we do now is multi-constellation. You cannot buy a smartphone with GPS only. If you can, let me know. I think it's impossible. I'll buy it from you if you can find one. So all smartphones are multi-constellation, and many of them are all constellations. All of the so many of the new smartphones indeed even track NAVIC right now, IRNSS, the Indian system that uses L5. So everything I've shown you is multi-constellation for at least several of them, or at least several of the available constellations. So that's not, so we already used up, we already played that card, if you like. And I think the answer to like, where does the solution come to that is we do want more measurements. So that part of the question is correct. The presumption is correct that more measurements help, but the more measurements come from doing smart things with L5, as I mentioned, and for the reasons that I showed you. So that's where the more measurements are going to come from. And one thing while we're talking about it, and I didn't dwell on because of time, but let me just point out this. That's maybe you didn't do this arithmetic lately. I didn't do it since a few months ago, and I was surprised at this lovely big number. There are 82 operational L5 satellites today. Isn't that fantastic? Thank you. GPS, QZSS, Galileo, Beidou, and IRNSS. All these different operators have been putting up satellites with L5, and so we have a tremendous constellation of L5 satellites available today. And so by properly exploiting that, I think that's how we reach the end game of the urban canyon problem.
Okay, great, thank you. One final question. What are the prospects for Google Live View and your other innovations working on iPhones?
I don't know. Sorry. I think it would be a wonderful thing, and if I can do anything to make it happen, call me.
Okay, that's a fair answer. Well, thank you, Frank, for your presentation today. We've had some good discussion from both of our presenters. We thank you for your time.